Okay, in this video I'm going to show you how to interpret the NMR for product B of the benzocaine synthesis. But before we do that, we have to go back and look at your product A NMR and make the assignments there so that we can compare what happened in product B. So this is the structure for product A. And you have basically a para-disubstituted benzene ring, which means down here you will have a pair of doublets. This NMR was taken using CdCl3 as the solvent, and we have to use a solvent that contains deuterium because deuterium is an isotope of hydrogen, but it has a different frequency. So the trace amount of chloroform, CHCl3 is the peak right here, and so this peak right here is our actual reference. You may wonder, well, where's the TMS at zero peak that you talked about in lecture what seems like a semester ago? We actually don't use TMS as a reference. We use the residual amount of protons in chloroform in the CHCl3 that's in CdCl3, which is only like 0.01%. We use that as a reference. So we see these two doublets. What other peaks do we see? Well, we see the NH, which I've labeled as C. This is the NH proton of the amide. And then we also see two CH3s. We see a CH3 attached to the carbonyl, and we see a CH3 attached to the benzene ring, which we're going to go ahead and, you can see I've labeled them E and D, but you might say, how do I even know that? We don't know that yet. So I have already filled this out. So in terms of assigning the doublets in the benzene ring, we've now gotten to a point in lecture where you've talked about electron donating groups and electron withdrawing groups. Well, now we can actually tell which doublet goes with which. So electron donating groups cause the doublet to be shifted to the right, to a lower chemical shift, whereas electron withdrawing groups push to the left. Now, you might say, but these are both electron donating groups. Great. The one that is more electron donating will be the peak on the left, and the one that is less electron donating will be the more electron donating group will be on the right, the less electron donating group will be on the left. So if I look at these hydrogens that are next to the nitrogen, and I look at these hydrogens that are next to the methyl group, in terms of priorities, the nitrogen is more electron donating, so therefore these peaks are the benzene rings, which I've labeled HA here to correspond to the protons, those two protons, and then HB next to the methyl group are these ones that I've labeled B. So you can go ahead and make that. You'll see there'll be a change in chemical shift here in a moment as we change these different groups around. So what we have is we have a pair of doublets for the para-disubstituted benzene ring. We have an NH, and then we have two methyl groups. In terms of looking at the integrations, now the integrations on the NMR spectrum are these numbers that are down here below the baselines. So it looks like we've got 19 and 20, and we've got 30 and roughly 30. If we go through and divide those, that's going to be 1, 1, 1.5, and 1.5. You would then multiply each one by 2, And so we would come up with 2H, 2H, 3H, and 3H. And so you'll want to do this for your part A spectrum. You want to show the ratios, show your ratios, and then convert those to protons. You don't have to worry about the NH. I didn't integrate the NH because it shows up wherever it wants on the spectrum. So some of you may have the NH peak kind of in the middle of this doublet. It may be to the right, it may be to the left. It depends on the amount of water in your sample as to how the NH moves around. And we'll see that in product B. Okay, so this is how we make those assignments. This is how we take the integration ratios. And this is how we would then say, you know what, I can't really see any impurities in product A. And I think for the most part, most people's product A's are pretty good. Now, remember that the two doublets are just a little bit above 7, just a little bit below 7.5. Now let's look at a product B NMR. And before I do that, remember what we did. We used, in product B, we used KMNO4 to oxidize. We did nothing to the amide group, but what we did was we oxidized the CH3 to a carboxylic acid. So if I'm thinking about what should happen is I'm still going to get a pair of doublets for the benzene ring, but then I'm going to lose one of these two methyl groups. I'm going to lose one of those two methyl groups because now that methyl group has been converted to a carboxylic acid. So let's see what we get. So here is the spectrum, and this is a pretty typical one for product B. Let me again write its structure out. But now we've oxidized the methyl group to a carboxylic acid. This sample is also has a tendency to be wet because the carboxylic acid group hydrogen bonds really well with water. And if we just let it air dry, even though this has been air drying now for 3 or 4 weeks, there's still a little bit of water. So let's go through and mark that. So this peak right here is H2O. This peak right here, between 12 and 13, that's where we would find our carboxylic acid. You might say, what about the peaks here at 10 or so? Good question. One of these is the NH of product B, and one of these is the NH of product A. So let's take a look at this spectrum. The first thing that we see is we see that we have two sets of doublets. We have a set of doublets between 7.6 and 8, and another set of doublets at 7 and about 7.5. Remember I said, remind yourself that product A was at 7 and 7.5. So these two peaks correspond to product A, and these two correspond to the desired product, which is product B. Okay. Also notice I changed solvent for this because with the carboxylic acid, it really doesn't dissolve in deuterochloroform that well. So I'm using deutero DMSO. DMSO has this structure. If you remember back to the aprotic or non-hydroxylic polar solvents back in SN2, DMSO was a classic one. This peak rate, let's go back. We'll blow that up in a moment. This is the DMSO peak. And I'll show you where that is in a moment. So in terms of marking the peaks, we've got a nitrogen for product A, the NH for product B. We've got our typical carboxylic acid peak, really nice. It is wet. There's a water peak. And then you can see that we have product A and product B. Now, if we look at the methyl groups, remember that in the case of the methyl groups, one of them was going to disappear when we oxidize the methyl group attached to the benzene ring. So let's go ahead and blow this up on the next slide and take a look at it. So here is the spectrum. This is the DMSO peak. I integrated it. I tried to get as quickly as possible. This is, since it's the larger peak, we'll call that A. That is the methyl group on the product B. These two methyl groups right here are left over from product B. Sorry, they're left over from product A. Now, which is which? Well, if we go back to our original spectrum of product A, we had two singlets of equal integration, which we should have because there's two methyl groups. They should give the same number of protons. If we now look at this, those two peaks are there. Now, what happened is that when we replaced the methyl group, when we converted to a carboxylic acid, the methyl group that is on the product, that's in the product here, shifted over. So over here we see a peak, but we don't see the corresponding methyl group of product B. So while product A has two peaks for the methyl group, the two methyls, one attached to the ring, one attached to the nitrogen, which this is going to be B, and this one's going to be C. So product A had two methyl groups of near equal integration, and if you look, this number of 10 is the integration for this peak. 10.95 here is the integration for that. They are right on. They're equal. So this, the reason I'm assigning this as B is because the methyl group that is in product B attached to the carbonyl just simply got shifted over, but there is no methyl group in product B because we converted the methyl group into this carboxylic acid. So that's how I can make my assignment. So the peak on the left was the methyl group attached to the benzene ring. The methyl group on the right was the methyl group attached to the amide. Okay, so that's how we can make those assignments. And I will give you for the problem for the NMR that you're gonna analyze for your lab reports, I'm gonna give you a blow up of this as well. All right, let's take a step back then. All right, so we have product A and product B, and that's totally typical of this reaction. If we would have continued on, we could have had a situation where we had product A, product B, and product C. We would have three sets of two doublets in the aromatic region, but we only made it to product B. Now, what are the percentages of product A and the percentage of product B? We have two ways to analyze that. Number one, if the two doublets on the left are product B and the two doublets on the right are product A, we have their integrations down here. Each of those corresponds to a total of 4 hydrogens, right? Because we've got the 2 hydrogens here, and we've got the 2 hydrogens here. Okay. So we've got those 2 sets of hydrogens. So all I have to do then is to treat these integration values just like I did in a GC experiment. So if I want to know the percentage of product A, what I'm going to do is I'm going to divide 6.69, which is the integration value of the 2 small doublets, and divide that by the total of 32.18 plus 6.69 times 100. So in other words, what I'm doing is I'm taking the integration of product A and dividing it by the integration of B plus the integration of A, which of course is the total integration. And so if I do that, I'm going to have, let's see, I need to, since I only have my phone here, I'm going to need to add up 32.18 and 6.69. So that total is 38.87. 6.69 divided by 38.87 equals times 100. So the percentage of A was 17.2%, which means that the percentage of B is equal to 100 minus 17.2, and that's going to be what? 83.8% pure. So this product is 83.8% pure with 17.2% of product B. Sorry, of product A. It's 83.8% product B, and it is 17% product A. We could do the same thing with the methyl groups if we want. Now in this case, I'm only going to compare the integration of the methyl group that's attached to the carbonyl. So I'm going to compare these 2 integration values. And so the integration value of product B is 43, and the integration value of product A is 10.95. So the percentage of A in this case is going to be 10.95 divided by 43.56 plus 10.95. Again, it's the integration of product B divided by the total integration. What do we do with the peak at 2 here? Nothing. Simply because there's no other peak to relate it to. So we're going to take in 43.56 plus 10.95 equals 54.51. So 10.95 divided by 50.51 equals 20% times 100. So it's going to be, so we get 1% product B, or product A in this case. So then it would be 79.9% B. You might say, why are they different? Well, it's just 2 measurements. So what you could do is you could take the average of the 2 measurements between the methyl groups and between the 2 doublets, and it's only a 2 or 3% difference. So that's the error in the measurement. But in this case, for this sample, it was 80%, roughly 80% or so pure, which may tell you something about why the melting point was so bad if you watched that video. Okay, so this is how we analyze it. What I would like you to do is I would like you for the spectrum, the proton spectrum I'm going to put up that everyone's going to use, make all the assignments, go through and determine the integration values, and the numbers over here, the numbers are going to change. So I will need to give you I'll need to give you the numbers here since they are a mess. So I will go ahead and put those numbers on the spectrum, but you're going to go ahead and divide through and then go ahead and make your assignments. But basically what we know is we know that product A was not completely converted, but it's about 80 to 83% pure, average about probably 81.5. So that wasn't bad, and that's very typical. So in your report, you're going to go ahead and show show the work on your spectrum that you get, and then include that in the results table, as well as in the discussion of the purity of the sample. Okay, if something here doesn't make sense, email me or put a question on Piazza and I can go back over it. But this is how we analyze product B in this experiment, and you can see that the sample wasn't completely pure, but again, that's pretty much to be expected.